Hello students, in this video we'll discuss Gershgorin circles for the eigenvalue problem for an n by n matrix. So let's let A be an n by n matrix. And then define a disk di called the Gershgorin disk by di is the set of all points in the complex plane C such that what? Such that z minus aii, of course that's the I diagonal entry of the matrix, is less than or equal to is important here, ri. And of course that's just a disk in the complex plane, and here ri is just going to be the sum over j not equal to I of ai, j. Okay, so we're in the same row, right? We're in the same row because I is fixed over here, and we're just summing over all the other columns that are not equal to I, right? And this, of course, is the radius of that disk. That's the radius. And so, of course, if we're an n by n matrix, I have, of course, n of these terms, right? And so the theorem of Gershgorin is that the spectrum of the matrix A, the set of all eigenvalues, is contained in the union. J goes from 1 up to n of these disks dj. Okay, so the spectrum is contained in the union of all these circles over here. That's a beautiful result. All right, so let's prove this result. And so let's let lambda be an eigenvalue. So here's how the proof goes. Proof, let lambda be in the spectrum of A, an eigenvalue. And V the corresponding eigenvector. Okay. Of course, then AV is equal to lambda V, right? So we have that AV is equal to lambda V over here. And I'm actually going to take V and construct another eigenvector. We're going to construct a normalized eigenvector. So define now, let's let U be V over the maximum I between 1 and n of the absolute value of vi, the ith component of that vector v. Okay? Okay, excellent. Of course, now the largest that ui can be in absolute value, the largest magnitude of the ui is going to be 1, right? Because you're dividing by the maximum, or the L infinity norm over here. Okay, so let's pick j such that, of course, the maximum is attained as well, right? Pick j such that uj is equal to 1, right? An absolute value. Okay, great. All right, now we're using the sum along the jth row, right? Then, of course, u is also an eigenvector. So now if I sum k goes from 1 up to n of A, now I'm in the jth row, so jth row, okay? Kth column. And then applied to what? Applied to the vector uk, right? And applied to uk has to give me lambda at uj, right? Lambda uj. So lambda uj. Okay, that's just by the definition of the eigenvalue, right? And so now let's take absolute values everywhere, okay? So I'm actually going to, one more thing I'm going to do over here, I'm going to peel off the jj entry over here. So if we peel off the jj entry, what can we say? We can say, therefore, that the sum over k not equal to j of what? Of a, j, k, u, k. I'm going to throw the a, j, j on the other side is equal to lambda minus a, j, j, and then uj. Okay? Now I'm going to take the absolute value of this equation over here. So take the absolute values of both sides. Now, therefore, the absolute value of uj times a, j, j minus lambda is less than or equal to the sum of these things over here. The sum of the absolute values by the triangle equality, k not equal to j, a, j, k, u, k, absolute values everywhere, right? And of course I have to put absolute values on these radius to make sure that the radius is actually non-negative, right? Okay, perfect. And so this, of course, these are all less than or equal to 1. So this is exactly equal to what? This is less than or equal to r sub j according to this definition, right? So this is less than or equal to r sub j. And this shows, of course, now this, of course, is 1. Usually is equal to 1, so this is exactly equal to j minus lambda is less than or equal to rj. And that says that lambda is in the jth one of these things, and therefore every eigenvalue is in one of these disks, and that proves the result. Okay, excellent. And so now what's a consequence of this? A consequence of this, let's get a corollary from this. A corollary is that let's suppose for all I, we have that ai in absolute value is strictly bigger than the sum over j not equal to I of a, or an ith row, jth column, like so, then a is invertible. Okay. And the proof, of course, is straightforward. The proof is elementary. The proof goes as follows. So proof, okay, the proof is that for any I, aii minus 0, right, is strictly bigger than what? Is strictly bigger than ri, which means that 0 resides in none of these disks over here, right? So in other words, 0 is not in di for every I, right? So that means that you are not in any of these Gershgorin disks over here. So you're in the complement of these disks over here, which means that you're in the complement, 0 is in the complement of the spectrum. So it says that 0 is not in the spectrum of A, and of course if you're not in the spectrum of A, that means you're invertible. So these matrices are called ones that are diagonally dominant, and so diagonally dominant matrices are invertible, and that follows from this Gershgorin Circle Theorem. Thank you very much.